Next speaker is Siddharth sa Yendra.
Yeah, sure.
We have a presentation, so please, Sai, whenever you're ready, you can start.
Yeah. So first of all, I loved Floyd's presentation before, and please bear with me for a few more minutes. I won't take a lot of your time. So hello everyone. My name is Sai Siddharth Satyendran, and I will be today be discussing about aerodynamic shape optimization using discrete adjoint and NURBS, especially for mesh deformation. So and a special hello to everyone tuning in from Italy. And yeah, let's just get it. So the motivation behind the study comes from my role as the aerodynamics lead for my university's Formula student team. I was responsible for the aerodynamic body design of our seventh generation vehicle. Given our limited R&D time, I needed a reliable simulation method to back my design, which would be presented during the design verification event at the championships as well. Initially, I used radial basis functions for mesh deformation, which is a standard approach, as we all know, for the aerodynamic shape optimization. However, while I was designing nose and restricting for the Formula Student car itself, I was working on a side by project, let's say, in parallel with the car. That is when I started questioning whether different techniques would improve meshing or offer more localization or enhance smoothness. This led me to explore NURBS, the non-uniform rational B splines. So let's just get into NURBS itself. Let's get get a brief idea of let's be comparing the two methods itself. RBS are primarily used to interpolate between values between control points, but they come with some limitations as well. For instance, changes in the control point can affect the entire mesh, making local control difficult. In SU2, RBS propagates surface deformations into the interior mesh itself. While they do ensure smooth deformation from surface to interior, they might inadvertently affect distinct regions in theory as well. NURBS, on the other hand, offer much final control over the specific regions using control points and weights. They generate very smooth surfaces and deformations, which are crucial for the surfaces where smoothness is critical, especially in formal student applications as well. While I was designing the nose cone for the seventh generation vehicle, I had a big strain which I had to huge bump, which was mistakenly designed by the team itself. So I had to make the body more aerodynamic whilst retaining the tube not protruding out of the surface itself. So that was a very big constraint, which was a local problem. So I could not properly do that with RBF. So that is when I went on for looking to block. While SU2 doesn't natively support nerves, integrating them into SU2 could provide enhanced control. This was the primary idea and the motivation behind itself, especially when dealing with complex geometries in aerodynamic shape optimization. Yeah. Now let's in this section jump into the on the schematics. In ASO, we aim to minimize the objective function, which is often an aerodynamic coefficient like drag. We adjusted the surface geometry via control points and propagate those changes through the mesh. The constraints we impose ensure that the flow residuals are not and the grid is updated accordingly. An optimization problem can also include multiple objective functions, as we know, including such as minimizing the drag while conserving lift. Geometrical constraints can be introduced without significantly increasing the computational time, increasing as maintaining maximum airfoil thickness and ensuring wing volume does not decrease as well. In the previous session as well, like we talks before, we were talking about using CUDA to increase the computational efficiency as well. So while we do that with RBF in mind, why not we introduce knobs into it as well so that we grow as a community while going forward and improving ourselves for more industry-wide applications, including the student community across India as well as in the world. So that was the major idea here. So then the workflow. So it is a typical workflow which I follow, which starts with the geometry description where I introduce knobs for mesh deformation, and then I went to the surface sensitivity calculation analysis, and then to the RAM simulation, and then iterating the process from there. So getting into nerves as in detail, nerves are a generalization of beta splines that use control points, weights, and knot vectors to define complex curves and surfaces. Each control point can be adjusted with weights, offering precise control over the geometry. The As you can see in the non-uniform, the word non-uniform represents varying distances between the knot points, giving us greater flexibility in shaping the geometry. The rational part is the use of weights, allowing for the creation of exact shapes like circles or ellipses. In mesh deformation, knobs, I believe, and I've been proven in maintaining geometric continuity, we allow for more smoother transformation than our. So why not go for our knobs? That seems the major question. And that's when we come into the performance metric and then the performance metric study, which I performed in my university here. The NURBS curve formula involves control points, weights, and beta spline functions, which are defined over the knot vector. They allow us to precisely control how each section of the mesh deforms. It's incredible, if you ask me, by offering greater flexibility in the optimization process as a whole. I also conducted, while now coming to the metric study, I performed a small performance metric study, let's say, by using knobs. I was not able to actually implement knobs in ANSYS in SU2 till now. I did it in ANSYS and I compared with the CFD study which I performed in SU2. So what I got was this. As you can see, the results show that while waves are easier to use, knobs excel in other critical areas such as localization, smoothness, local control, and memory usage as well. The only thing where you can see RBF ranking over NURBS is the ease of implementation. So that is exactly why we need to implement NURBS now in the SU2 community as well. I've been in the community for the past 2.5 years since I was the undergraduate student. And yeah, I firmly believe that we guys can implement it and make it far more faster than any other things because of the potential and the base of SU2 around the world. So this is what the aim and direction of the workflow of my study is going around. So my aim is to incorporate nerves would increase in the SU2's compatibility with popular CAD tools because I work in CAD a lot. My team works in CAD a lot. A lot of students here will use CAD a lot. So why not go into a more feasible MDO workflow which will incorporate nerves better? Creating a non-uniform. So our main objective was to create a non-uniform rational theta splines module in SU2 for mesh deformation and aerodynamic shape optimization, which is what we are currently working right now. And just to make it official, and with the university of mine, we created a group called Unlock Aeronautics, which would work towards and create this into a reality and publish a GitHub repository which will support the SU2 community. And that, yeah, we expect it to be up by next month, which will improve our horizons as well. So, yeah, yeah, if there's any questions, you can let me know. And I thank the Institute Foundation and yeah, thank you.
Okay, thank you very much. So the floor is open for question. I will repeat it to our speaker. So is there any question? Yes.
Hi, it's Ingo from THIAGARAJAR. I think 3 slides back you show like these comparisons with RBF and your score like it's like a performance score. How is this performance score evaluated?
Okay, so if you can go back by 3 slides.
Yeah, I am experiencing the same problem and I can't go back.
Well, wait, I'll do it for you. This one. Okay, so the question is that you're showing here a performance score. So the question is, how was that analysis carried out?
So yeah, so what I did was basically RBF using RBF metrics was taken out from calculations in app performing aerodynamic shape optimization in SU2 itself. But when it comes to nerves, I did it in ANSYS. So I had to compare these both. So yeah, with the same computational power and the same GPU which I performed, which was very comparable, and I feel like it served as a base which can be a proof of concept for SU2 to implement NURBS. So that was the main motive, and that is how I got the metric itself.
Yeah, what are the units on performance score?
Yeah. So the question is, what are the units on your performance score? So
Sorry, I couldn't get the question.
So the question is, what are the units on your performance score? So they all go in
So
between 0 and 10?
yeah, so what I did was basically put on from a scale of 0 to 10, which would, depending on the mesh size which I have given to each and everything, the RBFs and the nerve, I gave the same mesh size. And what I did was keeping RBFs as a standard, which I performed earlier with the NACA 0002 airfoil. So that I kept as a base. So with that, I put as 0 to 10. And then I compared it with another airfoil. That is what I did.
So some kind of relative measure. Sounds like.
Yeah, sounds like a relative measure, yeah. So the RBF would be underneath the NURBS.
Yeah.
Okay. So we don't get the comparison actually.
Yeah. So what I wanted to do was to show, because that this slide was just supposed to be like for a 10 or 14-second slide. So I thought by keeping the blue a little minimal or keeping it overlapped will be, the message will be clear. That is what my idea was.
Okay. Are there any other questions from the audience? No? Okay, so we can thank again the speaker.